Today I'll be talking about what the Hall effect is. Up to this point, we have seen how a magnetic field affects free-flowing charges. However, the Hall effect will explain how a magnetic field affects charges that are moving through a conductor.
Now, the Hall effect was discovered by physicist Edwin Hall in 1879. He discovered it while he was a graduate student at Johns Hopkins University. Hall determined that moving electrons feel a magnetic force towards one side of the conductor, leaving a net positive charge on the other side. We can see this in the picture shown. The current moves through the conductor, the rectangular shaped metal, and the electrons move to the right side due to the magnetic force. Consequently, the left side is positive. This separation of charge creates a voltage across a conductor. This voltage is called the Hall EMF, represented by the letter E or backwards looking 3. Remember that the EMF is the energy provided by a source, usually a battery or a cell. The Hall EMF is specific to a voltage being created by a magnetic field across a current-carrying conductor. Another important thing to note is that the units for the Hall EMF is volts, or V. Let's walk through an example of a conductor with flowing charges. This is our conductor. Notice that the magnetic field is perpendicular to the velocity, which is going left in the direction of the electrons. The magnetic field is coming out towards us. The current is flowing to the right, opposite of the flow of electrons. We know that the magnetic field is coming out because of the circle dots that we've drawn here. Now let's see what is happening to the electrons. The magnetic field is putting a force on the moving electrons, pulling them down. By the magnetic field pulling down the electrons, it is making the bottom part of the conductor negative. We know that the force is pulling them down because it is perpendicular to the velocity and the magnetic field. Therefore, the upper part is positive. The separation of charges creates voltage, which is the Hall EMF. Because we know the direction of the magnetic field and the direction of the current, we know that the Hall EMF for this example is positive. All right, here we have another example. And notice that it is similar to the last one we just did. This is our conductor. We have the magnetic field coming out towards us. Our current is still moving to the right, but this time we have positive charges that are moving to the right, instead of electrons that are moving to the left. Like the last problem, we have the magnetic field that is pulling these positive charges down. So those positive charges are going to be on the bottom. And the positive charges will still flow to the right, as you can see in this depiction. Now with the positive charges on the bottom, that means that there has to be a net negative charge on the top. We also know the direction of the magnetic field and the direction of the current again, meaning we can determine the sign of the Hall EMF. Based on those two things, we know the Hall EMF is negative this time. Let's quickly look at how we can derive the equation to find the Hall EMF. The charges on each side of the conductor cannot build up as much as they want. There is a limit. So to start, we can use the equation F equals Q times V times B, or magnetic force equals electric charge times velocity times magnetic field strength. The magnetic force will eventually equal the electric force, represented by F equals Q times E. We can substitute the electric charge times the electric field for F, and then the two Q's, or electric charges, on each side cancel. The electric field, represented by E, is uniform throughout, just like the magnetic field is, as well as the conductor itself. So we can use the equation E equals EMF divided by L to substitute EMF divided by L for magnetic field. Then we move the L to the other side and we have our equation. Hall EMF equals magnetic field strength times length times velocity, or E equals B times L times V. Alright, so now let's apply what we've learned and do a practice problem. The problem reads, a Hall effect flow probe is placed on an artery, applying a 0.1 Tesla magnetic field across it in a setup similar to the photo on the right. What is the Hall EMF given the vessel's inside diameter is 4 millimeters and the average blood velocity is 20 centimeters per second? So the first thing we need to do is figure out what equation we're going to use. Now the best equation for this problem is Hall EMF equals the magnetic field strength times the diameter of the pipe times the velocity. So we know that the magnetic field strength is 0.1 Tesla. We know that the diameter of the pipe is 4 millimeters, and we know that the velocity is 20 centimeters per second. The thing that we need to be aware of is what the units are in. So we know that the diameter of the pipe is 4 millimeters, but we want it to be in meters. So we'll convert that to meters, which is 4 times 10 to the third, or 0.004 meters. And then we know that the velocity is centimeters per second, but we want that in meters per second. If we convert 20 centimeters per second to meters per second, it gives us 0.2 meters per second. All right, so now that we have set up our equation, let's plug in our numbers. So we have Hall EMF is equal to 0.1 Tesla times 0.004 meters times 0.2 meters per second. That gives us a Hall effect of 0.00008 volts. Or an easier way to put it, it's 80 microvolts. And that's our answer. The Hall effect is used today for a variety of things. It can be used as a research tool to probe the movement of charges, their velocities and densities in materials. It can also be used to determine blood flow rate, as we saw in the practice problem that we did. It's even found in a lot of the common everyday things that we use. Computer printers use them to detect missing paper and open covers. They can also be used in computer keyboards and hard drives. The Hall effect sensors are commonly used to time the speed of wheels and shafts, such as the ones in the anti-lock braking systems. It can also be used to sense seat and safety belt position for airbag control. You know, that annoying flashing light that comes on if you start driving without your seatbelt on. The Hall effect is used for automatic toilet flushing, automatic sinks, and hand dryers. It's used for keeping your washer straight up so it doesn't fall over when it's spinning or washing. It's even used for sensor lights and cameras, the ones that dentists use, or even the ones that people put on their houses to see if there's any animal or person walking in their yard. There's a lot of things that the Hall effect does that we don't even realize, something that we should be grateful to Edwin Hall for discovering.
So just to recap, remember that the Hall effect is caused by a separation of charges in a conductor by a magnetic field. That separation of charges creates a voltage, which is called the Hall EMF, measured in volts. I hope this is helpful in learning a little more about what the Hall effect does. Thanks for watching.